Kinetics First Diffusion Season 3, Episode 7. I'm here with
Brighton Rogers, Chief Production Officer.
Brighton. It's so good to have you on the show. What are we going to be talking about today?
We're going to talk a bit about Charles Proteus Steinmetz. He is the author of these two excellent books. Well, I can speak to one. You just read the other one.
Yeah.
I will in the future. And we're going to start things off with a quick question from the audience.
Great.
And this is from Ash. And his question is, would you ever consider licensing or open sourcing the quantum kinetic well down the line?
Yes, that's a good question. And we certainly would. The first milestone project will be a licensable 20 by 8 intermodal container for radioactive waste and also remediation of rivers and mining. So we would probably just have it be leased out to a nuclear fission cooling reactor to clean their water, or their wet storage dock, or do radioactive cleanup of the Pasco River water on the coastline or on the riverside.
Yeah.
So yeah, the answer is yes. We would definitely, that would be our business model as a leasing operation for Quantum Kinetics, at least for the first 3 years, I would say.
Well, leasing equipment that we manufacture, as well as putting that out into industry so that others can apply these technologies to their own spaces, right?
Yeah, we'll probably start with just them leasing the equipment that we have that works.
Okay.
And then we'll kind of modularly lease the technology and teach them, like in educational settings, and kind of like Bell Labs did this a little bit, where they had the transistor. Mm-hmm. Come learn about the transistor.
And Steinmetz with GE.
And we'll get into Charles Steinmetz. I'm super excited, Brighton, to talk about Charles Proteus Steinmetz, because he is, AC power would not be what it is today without him.
Right. What a transition, by the way.
Oh, thank you, sir. Do I get rewarded?
Seamless.
Do I get to open my Red Bull?
You'd almost think we had a sponsorship or something.
Oh, well, maybe one day. But so Charles Steinmetz, who is this guy?
Yeah.
So he was a German guy that came over and as an immigrant to America, and he started working immediately with problem solving. Mm-hmm. And he's basically an interdisciplinary learner. He learned writing. He worked for wrote these newspapers in Germany. And then he got into mathematics and started learning about Oliver Heaviside. And he's the guy that did the telecommunications with the telegraph. But essentially, Charles Steinmetz is basically a borderline genius. But he was very easy to spot. Oh, he's definitely a genius. Sorry,
I'm going to give him a little more credit than that.
Well, he was a way beyond his time, because he was talking about things like imaginary loads, imaginary masses, which we'll get into.
Well, that's really relevant to the book that you just held up.
Right. This is
4 lectures on relativity in space.
Yes, this is a great book. You should definitely check it out. This goes back to, he was born in 1865 and died in 1923. He lived less than Tesla.
And he was definitely a contemporary with Tesla. He was specifically or primarily hired by GE to reverse engineer some of the stuff that Tesla was doing and figure out how to make AC power transmission work. Because at the time, Tesla wasn't really getting let into the big boys club, even though he was the originator of a lot of really neat stuff at that time that made our current power grid possible.
Yeah, he did the radio. He did the AC power. He fixed the commutator problem back in the day with his generator and made it a stator, and then the rotor spins inside of it, which is amazing. So, Charles Steinmetz was, you're right, in GE, they used the genius of Charles Steinmetz to back engineer Nikola Tesla's patents. Because what was happening was, when they would use Tesla's patents and they would wrap the transformers, they would turn it on and the thing would fry. It would just go in the puff of smoke. And they're like, what the heck? And so Charles Steinmetz was like, well, there's this thing called a hysteresis curve. So when a magnetic field, like of an electron, when a magnetic field grows, it has a pulsing, whoom, whoom. And depending on if you have a magnetic substance in the middle or if it's an air transformer, the hysteresis pulsing, whoom, whoom, is either fast or slow. And air coils, they go fast. They have a really high frequency. And if you don't catch that curve, that wave properly, your transformer will fry.
And iron core transformers, or coils, magnetic coils, store a lot of energy.
Yes.
So that's one of the things that he really talked about to a pretty good amount of depth in this book. And it was really exciting for me to see writing from somebody talking about some of the more important nuances about electrical behavior with the interchange of energy between the electric and magnetic fields and how those move and kind of act like a spring between each other.
How they create energy potentials, right?
Yeah.
And so for the audience, just for the basics, just to bring it down a notch, in electronics, there's only 3 things you should be concerned about in electronics. The resistance, which is how much effort it takes for electrons to flow in a wire or something. And then the capacitance, which is how much the electrostatic charge builds on a plate. Okay. And then the next is the inductance, which is the coil of wire around, which makes a magnetic field grow.
Right.
And each one of those has a very special thing called a phase angle, which we'll talk about later. That's the big thing he discovered, was phase angles. And I find it really interesting that his scoliosis of his back, because he was a 4-foot man who had scoliosis humpback syndrome. And I find it interesting because his big discovery is about the AC, because his back was curved like a wave.
Yeah.
And the scoliosis effect that happens in your spine, it makes a triangle. Like your spine normally is like a square, but each vertebrae, but his was like a triangle, which is like sine, cosine, tangent.
Like from the side.
Yeah.
The vertebrae were kind of pressed down.
Yeah, and it gave this angle like with a hypotenuse. That's why he had that weird. But that's the thing about the arc length and the phase angles of electricity and transformers is like this guy, he lived in his body the electricity design.
Yeah, it's kind of...
It's weird.
The world's a funny place sometimes, isn't it? He had some really profound stuff in here also about making sure to draw a clear difference between the presence of a dielectric or a magnetic field and the actual effect inside of the materials, because you have materials with different permeability and permittivity, and that's why when you put a piece of iron inside of a coil, you get a much stronger magnet with less current through that coil than if it's just air. That's energy storage in the circuit.
And the frequency drops too. If you put the core in, the resonance, the reactance and the resonance changes and it goes to a lower frequency. And that's why if you use like stainless wire around a transformer, it really drops the frequency down. It makes it more like an earth core where it has like Schumann resonance of 7.8. It's like boom, 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 boom. Like it's a really slow heartbeat. Versus if it had air inside the planetary core, it would be like, like, and actually in stars, there's stars that are really quick. They're called pulsars because they have, I would say that they have basically a water, a quasar. I'm sorry, I'm quasar, not a pulsar, a quasar.
Well, also another point there that he makes a lot of effort to cover is that topic of reactance, or basically how responsive an electrical circuit is to different kinds of stimulation. When you have mismatches, you were having transformers blow up. But he also has a lot of pictures in there of oscillographs. And this, I think this was early on when oscilloscopes hadn't really become a mainstream measurement tool. Like we have those in every college electronics lab to measure circuits and watch how they're behaving.
Garage now, like everyone has one.
I have one in my office, and I haven't used it in a while.
I know Tesla would have been like totally, floored if he could see the actual current and the voltage on a screen. I know he would have just been giddy as a schoolboy.
They were having to operate with a lot less detailed information than we have now, but they still figured out pretty much everything that we operate with now for our electronics circuits. But there were a couple quotes in these books, one that you wanted to read off relating to gravity, but then I also had one that I found really exciting to read about that's closely connected to what we're doing.
And this is what is this. I'm going to read about gravity, and this is from the general relativity lectures. And I want to make a point that Faraday, when he was writing in his journal, he said that when a coil of wire is discharged on a Faraday battery, that he wrote in his journal that there's something strange about this, and I think it has to do with gravity, is what Faraday said. I'm going to read to you what Charles Steinmetz said about gravity. And this, remember, this is an electronics guy. Here it is. Gravitation thus appears as a centrifugal force of an imaginary velocity. An imaginary velocity on the first sight appears nonsensible and meaningless. But it is no more than, for instance, a negative force, as in equation 10. A negative force inherently has no meaning, but we give it a meaning as representing a force in opposite direction. But just as a negative sign represents the opposite direction, so the imaginary sign represents the quadrature direction. That is, an imaginary velocity is a velocity at right angles, just as a negative velocity would be a velocity in opposite direction.
So, that's pretty technical. There's a lot of jargon there. So, it might be good for the audience to have a little bit more of an explanation of
and he does
what's
that
going on there.
In equation 10 here, it says, the equation F net equals ma? The first thing you learn in physics.
Mass times acceleration. Yeah, it's one of the basic relations.
In high school, in high school, the first thing you learn in physics is F net force equals mass times acceleration. But in his equation here, he says that F force equals negative m times a.
Yeah, so he's tying in the imaginary number sets, which are kind of a hard
negative mass
topic to wrap your head around.
Which is antimatter. He calculated just with math the idea that there's a negative mass going another direction before Paul Dirac came on the scene and found antimatter with his equations.
It's kind of the implied reaction force to something that occurs, because you have something pop into existence out of the Dirac Sea, which came into the lexicon a little bit after Proteus's
20 years
timeline.
About
was
20
it years?
Yeah, because he died in 1923, and then the Dirac Sea hit the floor around 1940, 1945.
Yeah, so that's your antimatter, that's your anti-proton, that's your anti-electron, or positron.
And it's crazy how someone who's a mathematician, electronics expert, is hinting at it without knowing it. And so that goes, why?
There's some foreshadowing there for sure.
My question to you now is, like, if he had this idea of anti-mass, why would he even think of that and even come up with that thought by studying electronics? Because you're the more math side of this, right? Because
to be able to glimpse into the mind of a super genius, I don't know how he made that connection. But it stood up and has been continuously involved in our deeper levels of physical exploration that we do. My quote from this book, again, I'm just going to keep pushing this book because I liked it so much.
I will say this. This is why we don't, this is, ladies and gentlemen, this is why we don't burn old books, because these books are valuable.
Yeah. So I'm trying to find that page that you had pulled up. Oh, there we go. So I was reading through here and I got a little quote early on in the book that kind of made me think. I'm like, is he saying what I think he's saying? And he said, thus far, the only source of cumulative oscillation seems to be an energy supply over an arc, especially an unstable arc. So here he's talking about when there's arc discharges in an electrical system, they seem to want to keep
going,
resonating. And when you're looking at an electrical circuit, it's got energy stored in fields around that portion of the circuit. Mm-hmm. And if that goes away, it gets discharged and released.
Like
it takes time for energy to kind of flow back in along the circuit. But when he was having these arcs kick off, they wanted to keep oscillating to the degree that they'd make things go boom in bad ways and make power shut down for areas. So he talks about this a little bit more, and I'm just going to go ahead and read this whole section because it's a really critical point.
But before you start, I have one question.
I'm getting carried away.
No, that's okay. That's good. What is the difference between an arc and a spark?
That one, I don't know, because I know you draw a difference between those all the time. You're like, spark and arc, and I'm like, okay, I don't really know what you're saying here.
Do you want me to describe it for you?
Yeah, please, go ahead and describe it. So I know we're using the same terms.
Yeah. An arc is when basically the electrons coming off of some surface, they're just kind of oscillating. They haven't shot across the gap like an amperage.
So it's kind of like a glow discharge.
The electrons are doing particle oscillation as an energy generator, and they're just going and they haven't gone anywhere. They're
just out in free space nearby.
Yeah, okay. It's like plasma. They're just trying to decide where to go. They come up and they look around and try to solve it, and they go, well, I can't solve it. I got to go back.
So I think if people wanted to find a good image of what we're talking about there with you said arc, right? That's arc. What you're called.
That is an arc, and a spark is when the electrons actually shoot off, and they hit the anode, and it damages it.
It's when that circuit becomes closed, and it's able to totally release closed, that energy. Yeah. So a good image of that is if you go and look for corona discharge on high voltage electrodes, it'll just have no connection. There's no circuit to flow through. It's just this little piece of wires at a really, really high voltage, and it starts glowing around it in kind of a little cloud, like it's got its own atmosphere.
I will tell you, that's interesting that you say atmosphere, because I'll tell you this.
I thought that as I said it too.
There is actually a dark glow discharge. There's multiple characteristic types of glow discharge, actually.
Like the sun, right? It's got its coronosphere, and then its ionosphere. It's got like layers to this cake or plasma cloud.
Yep, you got it. Everything in the universe wants to discharge.
Right. And then with the spark, you would equivalent.
It's death.
You'd basically call that what a lightning strike is.
Oh yeah.
On the atmosphere of the Earth.
It's high amperage discharging all at once. And by the way, back to the book, Charles Steinmetz, that's one of the things he discovered was how to do lightning arresters in industry. It's one of the things he worked on too. Right on. Go ahead.
Okay, so talking more, Steinmetz likes talking about this stuff because something he deals with or was dealing with at the time for power distribution was when you have a spark form, it creates a lot of noise and oscillation in an electrical system, and that'll go from one place to another, and when it goes from a line to a transformer, and then or from a transformer to a transmission line, it causes stuff to go boom. So they're trying to figure out how this stuff behaves, how to get rid of it,
how to dampen it, control it, all these things.
And he gets to page 123 of the book. He says in section 44, however, the formation of continuous oscillations from the recurrent oscillations is not a mere running together and overlapping of successive wave trains.
It's a lot of words. Like, yeah. All right. I only got like 4%. No, I got it all. But
I'll talk through it. Yeah. So what he's saying here is, like I was saying earlier, there's only so much energy in this section of wire, and you close the circuit and it goes, zzz, the energy's gone. It's been discharged. So it should take a certain amount of time for that energy to flow back into that section of wire from the rest of the wire.
Because the universe has to renormalize.
Yeah, it has to fill it back in. This is a pressurized system. Yeah. So you get rid of the pressure, energy has to stop flowing, and then it has to charge back up and then discharge again.
Doesn't it rebound back? It's like a tennis ball hitting another, like right. You throw a tennis ball at a wall and it bounces off and makes noise. Bong.
Right. So the point he's getting at here is, in order for these oscillations to keep going, at some point, these will occur frequently enough that they stack up and create high amplitude oscillations that are occurring at a much faster rate than that discharge and refilling cycle can occur based upon their measurement of the wire.
This reminds me of like what the stories of Oliver Heaviside were. They were in the telegraph room and there was an Aurora Borealis event outside. And they were doing telegraph, and then all of a sudden they just get shot with a bolt of lightning from the key machine.
Yeah.
And then they were like, "Whoa, what's going on?" And so they tried disconnecting the batteries that were there on the cells that were on the floor. They disconnected them, and they could still key to the next station without a battery. Because the Aurora Borealis was
charging the line from atmospheric
charge
electricity.
Was there? Yes.
Yeah. So I think this is a little different for the case of like forming an arc. So basically they kept running that over and over again, and they realized that this kind of resonant behavior of building up intensity of electricity in the circuit would not be occurring unless there was energy coming into that wire from somewhere that was not the rest of the wire in that circuit.
So if I'm understanding you correctly here, you're saying that there's one pulse, there's a renormalization.
Yeah.
But during the renormalization, somehow there's extra energy being forced in from the universe into the wire?
There's more energy. There's more energy coming into that wire to create that continuing ringing in the circuit than is being run through the wire itself.
Sounds like a resonant arc reactor transformer pulsing.
So they kept, I'm going to skip a good portion of this, but
you can check out the book. You guys can check out the book.
Later on, he says, thus essential for such a continual oscillation is the existence of a hysteresis loop, formed by the lag of the effect behind the cause. Such a hysteresis loop exists in the transient arc. And this is a beautiful image here of what a hysteresis loop looks like. And yeah,
the hysteresis is important because it's like the behavior of a heartbeat.
Yeah.
The magnetic field versus the electrostatic field, the inductor, the coil versus the capacitor, and how the electricity flows back and forth between the two during a discharge, like your heart, bump, bump.
And that's what principle every single internal combustion engine works off of. That's the principle that every pneumatic or hydraulic engine works off of. It's a differential in the amount of force required to move something one direction while it goes back the other direction.
Like a ball on a spring?
Right. Well, maybe kind of like that. I'm not connecting that, but...
Because there's inertia, right? Like even in this thing about this negative mass, there's a renormalization inertia. If a ball is on a spring, the ball would be the capacitance, and the spring is the inductor.
Yeah.
And the wire connection of itself of the material is the resistance.
Right.
And so if I pull down, it's going to go one, 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 one.
Yeah, but if you pull down and then pull down again at the right time...
Ooh, you get me all excited.
then you get this crazy resonant behavior in your system. And that's how...
That's a transient that gets controlled.
That's where this hysteresis in the transient arc comes from. which is an incredibly important piece of history for the science of electricity. And I think it's an incredibly underappreciated or maybe underknown phenomenon that we figured out almost 100 years ago now.
Yeah, and the arc reactor technology, it's so funny that the arc discharging and the arc reactor is named that, because a lot of the things that Steinmetz made, he came up with this idea of simplifying the AC signal for mathematics. And you mentioned this in the beginning, is that he made these things called phasors, basically phase angles, which a capacitor has a phase angle, and the inductance has voltage leads while current lags. And a capacitor, the current leads while the voltage lags. So it's the conjugate, it's the opposite. Right. And then resistance is just straight on resistance. Everything's in phase, right? And so in order to do the math, you have to use phasors, which is basically Pythagoras theorem, hypotenuse, sine, cosine, tangent. If you look at the equations in the book that Brighton shows, he just uses cosine and tangent and sine.
It's all circle math to describe the stacking of these things. And forget the guy's first name.
Charles?
No. Somebody else. Fourier.
Who did Fourier curve.
Wave analysis, and he broke up really complicated systems into a combination of sine, cosine, tangent. A lot of those, and a lot of that made huge contribution to the way Charles Steinmetz looked at oscillations and electrical systems.
Yeah, but I mean, it's really interesting how they in academia they explain electricity like water through a pipe. You have pressure, you have the diameter of the pipe is the resistance. If you have a smaller pipe, there's more resistance. A larger pipe, there's less resistance.
But it's almost more like water outside of a pipe.
It's like water flowing through. It's like weeping in
by the ether.
Sponsored by Ether. Very good. That was a good one, Brighton.
Thanks, Dayton Miller.
Yeah. Well, it's so great to see that, like, all of these great people from the past, like Oliver Heaviside, Charles Steinmetz, Nikola Tesla, James Clerk Maxwell, and
Faraday.
And I want to say this, that the idea of the Maxwell's demon way back in 1880 and 50, the founding father of electromagnetism, Maxwell, was writing about this demon that could break the laws of the second law of thermodynamics. He was hinting at it. He couldn't do it. He couldn't prove it because he didn't have semiconductors.
Didn't have the technical capacity at the time or manufacturing capacity.
I mean, he didn't even really know what a semiconductor was. He just knew that something was conductive or non-conductive, an insulator or a conductor, and that's it. And so we here at Quantum Kinetics are just basically we're on the shoulders of giants. We're just normal people that work really hard, but we have learned from the past and taken their ideas and just taken the next step. There's nothing strange about that.
Plus a willingness to look in the right places is also important. There's a bit of luck involved.
Which leads me to a question for you, sir.
The nature of luck is debatable, but...
Well, luck is when preparation meets opportunity.
Right.
And I'd say that we have a lot of luck. But the question I wanted to ask you about the word look. Would you...
as in, like...
Look at but like where to find
Make it dramatic. This is entertainment, guys.
It just reminded me of that squirrel that looks back and goes dun dun dun.
Yeah.
The where to look is not as intuitive anymore as it used to be, because like these old books, they're not like, you don't get this book at the university and say, hey, you got to read this book. You're given a textbook that the professor wrote, which costs $400. Because you're taking his class or her class,
right? And I think there's a lot of problems in our academia where it's like playing telephone line. Like a lot of these professors who are teaching electricity didn't have anywhere near the level of intimacy with the phenomena by personal experience of exploration that the guys like Tesla and Faraday and Steinmetz had. So So the way they thought about these things were very, very different, and a lot has gotten lost in translation. Plus, when people come along and restate these same ideas in different ways, you have a scientific community that is like a bunch of crabs in a pot trying to climb out. They're pulling the one that's almost out back down so frequently through the very action of the peer review process.
Wow.
It's like if you're
visual. Wow.
Right, you're creating something new.
Is that pot getting hot?
Nobody else has figured this out or seen this before, and you're trying to tell everybody, but people are like, no, that's not possible. And they've got these concepts of how things work crystallized into their mind as if we have the ultimate truth already, when the history of humanity and scientific exploration is that we don't and can't possibly know everything. So it's an exploratory process. We're finding new things that we didn't know about. So
it's foolish to even think that you know everything. First of all, like, to say that the academic edifice is the all-knowing, all-powerful God Almighty on planet Earth.
It's like, a replacement of one religion for another, in my opinion.
Oh, yeah. I would agree with that.
But kind of a very dysfunctional form of religion.
Well, it gets really kind of crazy because then you get this
I don't want to get too political, but...
I was just going to say that word. But, I mean, we don't need to say it because we already ever can imply that we know that, right?
Yeah.
Like the crabs trying to crawl out of the crab pot that's getting hot. That, I mean, say no more, sir. Say no more. Yeah. You win-win, right? You get it.
It's a pretty vivid image, but it's powerful and true. I think that's why it has so much weight.
You know, and I think that's why this discovery was made by, quantum kinetics, because, we think outside the box. We're trying something new. We're trying something different. If we keep doing the same thing over and over and over and expect different results, I mean, that's a definition of insanity, right? So, like, if someone's trying something different and in a unique way and being persistent, that's how innovation comes about historically.
Right. And that innovation can't be suppressed forever. It won't be.
It won't be.
It won't be. It simply can't be. And I mean, it's just an ongoing process of like, all right, well, we're designing the details, we're working through this stuff, creating plans, getting ready to go into action.
Yeah.
And it's a very, very detailed and work intensive process, but it's also very rewarding. I've deeply enjoyed we've been doing all this stuff.
We're just beginning, sir. Like, this is really like just the tip of the iceberg. And when I spoke with the COO of Google way back in 2020 over dinner, he said to me, the invention itself is the easy part. The commercialization of the invention is the hard part.
Because then you have to convince a bunch of people who don't have any frame of reference to understand what you're talking about. You're literally walking in as the crazy homeless guy. I've got fusion in my pocket watch.
Yeah.
And you very well might have that fusion in your pocket watch, but it takes some time to bring people around to your side, and it's learning how to have meeting of the minds with people who don't quite see what you're seeing. And it takes a lot of work to help them see it too.
It's a brain trust, right?
Yeah.
You have to have trust in the idea. You have to have trust that you've done your due diligence. And we sure have here at Quantum Kinetics. We've taken 10 years of our lives and dedicated to science and the discovery of being honest, and kind of humble and not saying anything until it was absolutely positively time to say something.
Right.
Like, we got published in peer review with NPJ Nature and Clean Water with 3 reviewers with high acclaim. Like, we've never seen this technology before. This is an amazing, device. We need to see this device everywhere deployed in the whole world. You're definitely going to get published, and we're super excited. And when peer reviewers tell you that, and then you wait 2 years to even say anything in press releases, we waited 2 years. We got published for the world record in nuclear fusion for holding 150 million degrees on well water and seawater for 8 hours, 6 consecutive tests in a row with different electrodes, aluminum and stainless. We still hit those temperatures. Did we say anything? Nope. We stayed quiet.
Not for a while, yeah.
We stayed quiet for 2 years. Only when we did the uranium test with radioactive rad waste and transmutated the uranium into tungsten, thorium, and lead and reduced uranium by 80%. That
24 hours.
Correct. That is when we knew we can no longer be quiet. We have to spread the word and scream it at the top of our lungs because we got it. And we can turn lead into gold too.
I was just going to slide that one in there.
Actually, I'll go ahead and just tell the audience, like, in astronomy, there's only one way to make gold. You want to know what it is? A neutron collision. Neutrons colliding with each other neutrons.
Neutron flux.
Or knocking off protons.
Which is one of the things that is considered the gold standard for fusion.
Alchemy.
Is neutron flux. Mm-hmm. And we've brought this up before, but I think it's worth repeating, is our reactor is doing its stuff inside of water and inside of other materials that do an excellent job of slowing down and stopping neutrons. So when we're measuring stuff from the outside of the device, it at the levels where we're measuring X-rays, we're not seeing neutron flux outside of it. It's safe for anybody standing nearby it.
Yeah,
it's not a problem. But then we're seeing changes in the elemental composition of the fluid that we're running through the device.
You bet. That
can only happen, as far as modern science knows, with neutron flux.
Which means
we have
nuclear fusion.
Nuclear fusion, guys. Yeah, and it's working continuously in our device.
And I'll say this too, Bryden. When we detect the X-rays on the outside of the Delrin of the reactor, we're detecting X-rays in the air. Like the air around the reactor is renormalizing to what's going on inside the reactor.
Right. And comparatively to like an X-ray machine at a hospital, these are very low energy X-rays. They're not traveling the same distance, right? Well, some of them are higher, right?
I have a great transition for that. So Nikola Tesla, and this is the big thing about Nikola Tesla, he made an X-ray machine where you could stand in front of the X-ray machine and not die. But if you had the GE X-ray machine and you stood in front of it, you would go to the grave because it was like 150 keV to 250 keV X-rays. It would basically kill you. Yeah. But Tesla had a lower energy X-ray machine that you could stand in front of it and it wouldn't kill you. Wait a minute, what? That sounds like our reactors.
There's some similarities here in some of the results we're getting to some of these people in the past.
Historic.
They just, and that was well before the concept of nuclear fusion was out in circulation.
Right.
Because this was even pre
1910, 1920.
Yeah, so that was before the Manhattan Project.
Oh, Manhattan Project was 1943 to start, and then they finished in 1945 with the bomb, Trinity bomb.
I had it in my head a decade earlier than that.
Then the transistor came on board in 1947-ish, right after that. Because, I mean, to trigger the Trinity bomb, they had to have a sequence of firing mechanisms that fired all at once to fire into the internal cavitation.
So that was a huge improvement and huge advance in electronics at the time to be able to get that kind of coordination.
And synchronization.
synchronization.
Can you imagine, like, all you have is a switch.
Yeah.
And all you have is a relay.
Right. Well, that'd be trivial now with the technology we have.
And, relays, the arm relay between when you fire it down and the solenoid has to fire, there's a lag. And so now all of them would fire.
So you have manufacturing differences. That was an enormous technical accomplishment at the time, especially considering a lot of that stuff was mechanical.
I want to say that maybe they had a pseudo transistor for the Manhattan Project. I think that they didn't tell anyone.
You think they
that's conspiratorial,
to make that work?
But I think they may have figured out a very Helmholtz resonator style triggering pin.
All right. Well, that might be good for another podcast on its own.
There's no information on that. I just made that up on that part. But I will say this.
Let's do the seance and talk to the ghosts. Find out. Because none of those guys are still alive these days.
Dude, everyone's gone, dude. Everyone's gone.
They're all
And this is
that record kind of went to the grave with them.
Of course it did.
Yeah.
Of course it did.
Well, it's probably in a secret vault somewhere, a record of what they did, but
well, I mean,
that might come out.
There's some electronic devices that are national security. Like there's certain I'm not going to get too deep into this, but there are certain electronic devices that are basically national security, and they're the size of your pinky, but they're super classified, and they're super duper rare. And Israel actually stole 1,000 of them once.
Oh, no shit.
Yeah, and they got in big trouble for that because they wanted to make their own bomb. So, again, to fire a thermonuclear bomb, you have to have a certain pin firing device.
Okay, so some pretty specialized stuff. I guess no surprise there.
Well, I mean, we're able to do nuclear fusion sustained at small little like pulses, controlled.
Right. Yeah.
Same thing with a transistor.
Now we can.
And I would say that people in the past in special projects probably knew about some of this stuff, but those are so deep, dark projects that, they're not going to come to the light of day.
Right. Stuff that takes until now for it to become a little bit more mainstream for awareness.
Well, the reason why it needs to come out now, Brighton, is because we actually have to do something with it. Like we actually have to save the environment. We have to stop the rad waste. For example, 2025, they're dropping. A judge just cleared a private nuclear fission company. They're going to drop 45,000 gallons of rad waste into the Hudson River. Okay, this is where money over people. What?
This sounds like a setup or precursor to another Teflon manufacturing problem, because at the time when they first started manufacturing it, they were just releasing the byproducts of the manufacturing process into the environment. And holy heck, a lot of people got poisoned and had a lot of problems, and a lot of cattle, and that was just a disaster.
Now,
it's like of a very similar scale to how asbestos was before we started learning how to handle it more appropriately.
Or smoking.
And it's not to say that the thing itself is evil. Like, Teflon's a hell of a product.
It is.
It's one of the few things that can hold up in a lot of industrial and processes and environments. It's a great gasket material.
Try machining it. It's kind of a hard one to machine.
Yeah, is it kind of slippery? I think I've heard about that before.
It slips.
And same with asbestos. It's extremely fireproof, but you sure don't want to breathe it in. And it's similar with fission. Like, power without a bunch of airborne pollutants from boiling steam from a spicy rock. That sounds pretty cool to me. Pardon my French, but we also have to deal with the byproducts of these things responsibly. And up until now, nobody's known how to deal with it other than put it in a tank, hope the tank doesn't break before you come and check on it again in 20 years, and just keep doing the same thing. And we have an option for dealing with that doesn't involve allowing it to slowly release into the environment until we don't care anymore, or until our civilization collapses.
We don't want that. Like, that's the thing about this is this technology is now hope. This is a solution to big problems, not just the hydrocarbon levels of planet Earth's atmosphere. We can cleanse that now too. We can do rad waste. We can do nuclear energy too, which we figured that out. And so the way that Quantum Kinetics is positioning ourselves as an economic impact to the world is that we're going back in time first. What can we fix with nuclear fusion that the past of nuclear fission damaged? We're going to do the rad waste cleanup. We're going to do all that first.
And other people who are in industries that would be classically considered competitors, like, if we can deal with rad waste, suddenly we've solved the PR problem for fission.
And they can keep going.
They can keep going. They can make 100,000 more nuclear reactors for fission power.
Sure.
And we can get cheap fission power throughout the world and have no issues
Oh, don't have a
nuclear
meltdown.
Waste.
Don't have a meltdown. And that one's a tough one.
Yeah, that's a tough one. I'm convinced that they've done a lot to improve that safety.
Did you hear about
I would
Japan?
call myself an expert.
Did you hear about what happened in the Fukushima plant recently, like 3 weeks ago?
No, I didn't.
Yeah, they tried to restart the reactors.
Oh, okay.
And it wouldn't fire up because the alarm system went off. Okay. And they were like, they had to shut it down. So ever since 2011. So this has
been a long ongoing process to get it back
I don't think they're ever going to
get
back on, bro. I think it's done. I think Fukushima's power plant is done because in 2011, the Fukushima power plant blew because it overheated. Yep. And it's been 2011 since that happened. How many years is that? That's like 20. No. Oh my gosh, that's 15 years. 15 years has passed. And they're just now restarting the reactors that were not damaged. And when they restarted the reactors that were not damaged, the alarms went off.
Yeah.
And they had to shut it down right away. And so TEPCO
they got some gremlins in the system.
There is something going on either hydraulically or energy surge wise. There's something happening at Fukushima's power plant that they can't even solve.
Okay.
And that just tells you a whole heck of a lot about nuclear fission, that we got problems, man.
Yeah.
There's better ways, dude.
There's a lot of options on those fronts, but fusion kind of is that ultimate temptation or desire there. Is like when that thing gets working, if you can run fusion like we can with normal water in a reactor.
Arc reactor, baby. Fusion on demand.
The potential for applying that and just helping things in general run smoothly in society, civilization, is like, sounds pretty rad.
I'll say, I've said this.
Not radioactive, but
everything about nuclear fusion is great. And the more that we play with it and the more we learn about it, Brighton, the more we realize that it kind of solves everything. You know, like when you're a pole vaulter, right? Yeah. Like when do you remember when you first started pole vaulting? You're like, I don't even know what pole to carry. I don't know what the weights mean. I don't even know my run.
There's a lot of details that just, you have no idea what to do. It's like learning to walk again. Have you ever watched a little kid learn how to walk?
Toddlers.
It's the same process, but now we're doing that process with fusion on a much grander scale with a lot more people involved.
It's exciting to be on the forefront of the technological advancements of the human race. This is not like a new pen or a new lighter or, a new vehicle. No, dude, this is a frontier technology.
It's a waypoint or maybe a milestone.
Brought to you by the 20x8 intermodal container, Quantum Black Box.
Right. We got to get that thing running soon here.
Yeah, we're definitely ramping up for it. We're gonna have a really cool prop for you guys to check out on season 4 when we come back after Randall. But,
so is Randall coming on next? That's the plan.
Maybe Jason, maybe Randall, but I think it depends on who wants to do it. But we got some really cool props coming up for the next season 4, and we're basically the longest running nuclear fusion podcast in the world. And thank you for coming along for this. It's really exciting for us. And thank you for learning with us. We got 12 minutes. Is there anything else you want to say about Charles Steinmetz, nuclear fusion? Anything else that can come off your head?
I think we've covered everything I came here to talk about today. And certainly with those few quotes and references and a little bit more of the technical discussion, I think we've given them plenty to chew on.
I think so too. Yeah. And as we close up, I want to say thank you, Brighton, for coming along for this amazing journey with us at Quantum Kinetics.
Always fun.
Yeah. I know you have a lot of big ideas, and we're going to really have a lot of fun. So thank you guys so much for coming along for this amazing journey and all of your support. And thank you for your subscriptions. And if you haven't already, go ahead and make sure you like this video. But if you have any questions or comments or thoughts, go ahead and hit them up on the comment section. And always remember, fusion is love, and love is fusion. You don't have to force it.
It just happens.
Right here, buddy. High five. All right. Thanks again for tuning in, and we will see you on the next one. Take care, everyone.